let's now proceed to the second part. And if you're wondering, can you use deep neural networks on nuclear physics topics? This is it. Let's watch Denny discuss this problem with us.
Thank you so much, Dr. Lim, for the invitation and also for giving me the chance to share our works in RCNP. Okay, so the topic of my discussion is distinguishing near threshold enhancement using deep neural network. And this work was actually published just last month in Physical Review D. So also this work is in collaboration with Yoichi Ikeda, Toru Sato, and Atsushi Osaka of RCNP. And let me start with the motivation. Okay, so first, why do we want to distinguish this kind of enhancement? So usually in particle physics, especially in scattering experiments, people observe these peak structures that are usually happening near some two-body thresholds. So these two-body thresholds are actually the energy, where you can have two particles coexisting, this at rest with respect to their center of mass. And these peak structures can have different interpretations. So I tabulated them here on the left side. So first, they could represent compact unstable hadron, which is very important when you're trying to understand how hadrons are formed in QCD, that is confinement. And not all these peak structures correspond to this elementary particle or hadrons. But also another possibility, because they are very close to this two-body threshold, is that they may just be dynamically generated states. So this means that if you have several channels of scattering, it is possible that some of the bound state are just moved out from the real axis and produces a peak structure in the scattering region. And another possibility is that it might just be a virtual state. So that means that the two-body hadrons, for example, these two particles here, could also have an attractive potential, but this attraction is not strong enough to form a bound state. And the last two are kinematical effects. So it has nothing to do with the production of new particles or production of bound state, but it's just merely due to the, so for example, the rescattering process, which is happening during the triangle singularity, or just a threshold cusp due to the opening of new channels in the particle creation. So ultimately, we wanted to address this wide varieties of possible phenomena that explains this near threshold enhancement. But for now, I will just be dealing with the simpler case, that is the Nucleon-nucleon scattering. It's only one channel. You only have two particles that are scattering. And in an S wave or zero angular momentum scattering, you can actually have two possible scattering cross section. So the first one is the S wave for the spin singlet case, where the wave function of these two particles are antisymmetric, and you have the spin triplet state. Okay, and actually one of them can produce a bound state, and we will be using neural network to do this distinction. Okay, so just to give you the outline, I'll give you a short introduction about nucleon-nucleon scattering, and I'll describe the proposed method that we are using. And also I will describe how we generate the training dataset, because this is a deep learning method. And also I will talk about how we validate our neural network by using an exact solvable model, where you can get an exact S matrix. And then we apply this to the actual nucleon-nucleon data. And then I'll give a summary and outlook of our future study. Okay, so let's start with the nucleon-nucleon scattering. So imagine that you have two particles here. So in particular, let's say this one is a proton, and then this one is a neutron. So they have momentum P in the center of mass frame. And you could also describe the scattering phenomena in terms of the center of mass energy. Mu here is the reduced mass of the two particles. Now, what we know about this neutron and proton is that they can form a bound state, which we call the deuteron. And we know that this bound state exists. And in fact, we also know its binding energy to be negative 2.2 MeV. But in most cases, this bound state is not directly observed in scattering phenomena. So what we wanted to do is to map the existence of this state by looking at the scattering region. So here you have the scattering cross-section, and I have here the two plots for the different partial wave amplitudes. So this is the only thing that we can observe in experiment, that is the scattering energy is larger than zero, that is the scattering region. And E equal to zero here corresponds to the threshold where the two particles are practically at rest. Now in scattering theory, a bound state such as the deuteron correspond to the simple pole of S matrix, that is a singularity of the S matrix. And when we talk about S matrix, you can think of this as the coefficient of the outgoing wave. And at the pole, then this means that the dominant contribution of your wave function is coming from this outgoing wave. Now, since it is a pole, then the momentum here, the effective momentum here, can be replaced by that pole value. So here I split that into real part and the imaginary part. And you will notice that if the imaginary part of this momentum pole is positive, then you have a bound state. This is exponentially decreasing spherical wave function. So you have a bound state here. So the question is, can we deduce the existence of this bound state from the scattering region or observations? So actually we can. It has been done before. So what they do is you perform a parameterization of the scattering data, and then you do some analytic continuation. So of your scattering parameters. So for example, energy or momentum. So if you do that, it is possible that you can develop or form a pole somewhere in this inaccessible region of the scattering experiment. So for the case of the deuteron, we expect the scattering cross-section to have a singularity somewhere around this binding energy, which is below the threshold. Okay, so that is actually being done. But another problem is this. So in addition to the bound state, where the pole is located on the positive momentum imaginary axis, you could also have a pole in the negative imaginary axis. And if you look at this expression for the spherical wave function, k sub I here is negative, which means that your wave function is not normalizable. So this is not really a physical state. But nevertheless, you can also have your enhancement of the scattering cross-section at the threshold. So there are two possible ways to enhance your scattering cross-section. One is through the presence of the bound state pole, and the other one is through the presence of a virtual state pole. And only the bound state pole is a physically relevant state here. So we wanted to address this question. So can we distinguish bound and virtual state enhancements, in particular at the threshold? So we do this by using deep learning. So this is our proposed technique. So first, we will generate the data set, the training data set, using the general properties of S matrix. So in particular, these are just unitarity and analyticity. And then we use different architectures for the neural network, where the input is the scattering cross-section, the one that they obtain from the scattering experiment. And the output will be just the assignment of what causes the enhancement. So in this case, I will just be using two outputs, so the bound and the virtual state description. Now, in order to study the performance of our neural network, we'll be using an exact model to check the accuracy of prediction, and then finally apply this to experimental data. So let me proceed to the generation of the training data set. So this is the basic idea. So the S matrix here is written this way. And in proposing this S matrix model, we only considered two principles here. So first one is the analyticity. So this means that your S matrix should not have any poles in the first quadrant of your complex momentum plane. And this has something to do with causality. So that is, there should be no scattering if the incident particle is not yet in collision with the target particle. So no poles should be present on the first and third quadrant. So second, we also have the unitarity, and this is quite familiar to us. It is due to the conservation of probability, or in equation, you can write it this way. So since this is a single channel, then our S matrix is just a single function of P. Just take the complex conjugate for the Hermitian conjugate. So this is our proposed S matrix model to train the neural network. So the relevant pole that will be responsible in producing a bound state pole or virtual state pole is summarized in this factor. So I just need this P minus I gamma near. Gamma near here will be the red dot that can be adjusted or can be chosen near the threshold in the momentum plane. And because of unitarity, you can already tell what numerator should you put because you have to satisfy this unitarity. Now, I also put some background, singularity background here represented by a pole, but this pole is only confined in the negative imaginary axis of the momentum plane. And then finally, I will put some background here, which is supposed to be analytic. So I'll be using the inverse tangent function. But of course, this inverse tangent function upon analytic continuation will develop these two branch cuts on these two parts, strips of the complex momentum plane. So from the S matrix, you can calculate the scattering amplitude using this formula. So this will be the input of our neural network. And then we'll just simply choose random values of our parameters here, for example, eta and lambda within this region. Also, gamma near will be chosen very near to the threshold, and gamma far will be chosen so that it will always be farther compared to the gamma near. So these are the number of parameters that we have produced. And in total, we have 4 million input-output data points that will be used for the training. So, and by the way, the output is just based on the sign of gamma near. It doesn't really depend on the other parameters. Okay, now let me show you the training performance. So I hope this slide is big enough. Okay, so let me just describe this. So this is the vertical axis of all these graphs corresponds to the accuracy of predictions. The blue curve that you see, that is for the training data set. And the orange one is for the testing data set. So this 4 million data points are actually separated into two, 80% of which are used to optimize the weights and biases of the neural network, while the other 20% is for the testing. So we hide that from the network. And these are the performance. Now, I also have actually have 6 models here. So the notation that you see above there, for example, this one 200, that is 200 points for the input data set. So for each energy, I have the scattering cross-section value. And then the last number that you see here, that's 3. It is supposed to be 2 for this case, but in our paper, we use 3 possible cases, but it's still okay to use 3 here. Now, in the hidden layer, we have 250 nodes for this model and 100 nodes for the second hidden layer, and then you have the rest. The name that you see here are the optimizers that I used to optimize the training. Okay, so these are the results. Okay, now we have a deep neural network, actually 6 deep neural networks that we wanted to use to apply for the Nucleon-nucleon scattering. But I want to test them using a different model. So here I will be using the separable potential. This is quite popular in the community. So this is a separable potential. From this potential, you can plug this to the Lippmann-Schwinger equation, and you can get an exact form of your S matrix. Okay, now I think I have to accelerate. So let me just proceed. So what I did here is using this separable potential, I produced 100,000 validation points to feed to my neural network and verify if it can predict correctly the nature of the pole. So the important parameters here is the lambda, which is the cutoff parameter, which we will vary in the testing scheme. So this is the result for the 6 different models that I have used. So what you see here is that each horizontal line here corresponds to 100 data points, and the value on the horizontal axis corresponds to the cutoff parameter, that is the capital lambda, which is the parameter of the separable potential. So what we see is that if this gamma or lambda is very small, we have very poor accuracy for the prediction, and also poor accuracy if the lambda is also very large, generally for all the different models. Well, actually, the reason why this is not accurate enough is because of the presence of the background singularity, which messed up the scattering cross-section near the threshold. And also this bad or poor accuracy on the large values of lambda is because of the negligible effect of the background. So actually we need the background in order to distinguish virtual and bound state enhancement. It's because of this reason. Okay, so now let us apply this to our nucleon-nucleon scattering data. So I feed these two data points or these two cross sections to our neural network. And all of them are actually, the neural network was able to give the correct nature of poles for all of these models that is used to fit the data. So let me just summarize. Okay, so we have here the deep neural networks are trained using unitarity and analytic S matrix. And the presence of zero of amplitude and background singularity affects the prediction of our neural network. And this is because of the absence of the other features that might be relevant for the scattering cross-section. So we might need a more sophisticated S-matrix model for better accuracy. And finally, we got correct predictions for nucleon-nucleon system. So which means that unitarity and analyticity are sufficient to deduce the nature of pole. And these are the future plans that we wanted to do after this work. So thank you for listening.
All right. Thanks very much, Denny. So we'll have you in a few minutes again for the Q&A. Now we're going to switch to another mathematical system. So so Alfred's work is quite interesting. Many of us are familiar with a liquid-gas interface, and I think it's gonna be fun watching how it is modeled.